General Lecture Research STEM Integration. Second, let us greet and pray to our beloved Prophet Muhammad SAW, who had brought us to the path of light and left the darkness in this life. The Honorable Professor Julian Roig, PhD, as our speaker today. The Honorable Dr. Hartono MAS, the Dean of the Faculty of Teacher Training and Education, Sriwijaya University. The Honorable Dr. Ismet, Magister of Science, as the Vice Dean for Academic Affairs, Faculty of Teacher Training and Education, Sriwijaya University. The Honorable Nyimas Aisyah, PhD, as the Vice Dean for Administration and Finance Affairs, Faculty of Teacher Training and Education, Sriwijaya University. The Honorable Dr. Rizwan Jainuddin, Magister of Education, as the Vice Dean for Students Affairs, the Faculty of Teacher Training and Education, Sriwijaya University. The Honorable Dr. Ketang Wiono, Magister of Education, as the Head of the Mathematics and Natural Science Education Department. The Honorable Dr. Randus Kodri Madang, PhD, as the Secretary of the Mathematics and Natural Science Education Department. The Honorable Dr. Effendi, Magister of Science, as Coordinator of the Chemistry Education Study Program, Faculty of Teacher Training and Education, Sriwijaya University. The Honorable all the faculty members of Faculty of Teacher Training and Education, Sriwijaya University. The Honorable all the lecturers and students of the Faculty of Teaching and Chemistry Education, both those who are present at the venue and those who are present online. Last but not least, all the committee of the public lecture today. Ladies and gentlemen, I'm Suryana Dewi as the Master of Ceremony on this nice occasion. Let me deliver the structure of the event today as follows. The first, opening. Second, singing national anthem, Indonesia Raya. Third, the speech from the Dean or Deputy Dean or Head of Department. Fourth, public lecture delivery. Fifth, discussion. And the sixth, closing. Ladies and gentlemen, let's open this event by saying Basmala. Ladies and gentlemen, let us come to the next agenda, which is singing the national anthem, Indonesia Raya. Audience, please rise. Audience, please be seated. Ladies and gentlemen, now we invite Dr. Ketang Wiono, Magister of Education, for the opening speech and later open the event officially. To Mr. Ketang, time and place are yours.
Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning everybody. Yang kami hormati Bapak Ibu dosen, terutama Prof. Tatang hadir, Pak Dr. Effendi selaku koordinator program studi pendidikan kimia, dan seluruh mahasiswa. Good morning Indonesia Time, Prof. Jil. Puji syukur kita panjatkan kehadirat Allah Subhanahu wa Ta'ala. Pada pagi hari ini kita bersama dapat hadir dalam acara kuliah umum program studi pendidikan kimia yang luar biasa. Permohonan maaf dari Bapak Dekan FKIP UNSRI yang tidak bisa hadir di tengah-tengah kita. I'm sorry, Prof. Jil, I'm from home here. I am head of the Department of Mathematics and Natural Science Education, representing the Dean of Faculty of Teacher Training and Education, Sriwijaya University. I would like to welcome Prof. Jil to the Chemistry Education Study Program, Faculty of Teacher Training and Education, Sriwijaya University, in General Lecture of STEM Education. Nice to meet you, Prof. Jil. I hope hopefully this collaboration will continue in the future and the next event in Sriwijaya University. Bapak Ibu hadirin yang saya hormati, atas nama pimpinan Fakultas Keguruan dan Ilmu Pendidikan Universitas Sriwijaya, kami mengucapkan selamat kepada program studi pendidikan kimia yang hari ini telah berhasil melaksanakan event atau kegiatan kuliah umum internasional dalam rangka dalam waktu dekat ini program studi pendidikan kimia akan melaksanakan reakreditasi. Mudah-mudahan bisa mempertahankan akreditasinya dan meningkat nanti menjadi akreditasi internasional. Dengan mengucap Bismillahirrahmanirrahim, marilah kita buka acara kuliah umum pada pagi hari ini dengan bersama melafazkan basmalah. Bismillahirrahmanirrahim. Thank you, Prof. Jil. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much for Dr. Ketang for his speech and officially opening this general lecture. Ladies and gentlemen, now we come into the main agenda, that is general lecture in research STEM integration by Professor Julian Ruik, PhD. And to lead the general lecture, we will invite Professor Dr. Andes Tatang Suheri, MA, PhD as moderator. To Professor Tatang, time is yours.
Okay. First of all, good morning, Mr. Professor Gil Rohing. What should I call you, Mr. Gil? Or
Professor Jill is just fine.
okay, Professor Gil. Okay, I would like to introduce you to all audience. First of all, about your bachelor from University of Southampton, UK. Kemudian MS from Physical Chemistry, University of Arizona, and PhD in 2002 from University of Arizona. A lot of paper has been published with Mr. Gill, Professor Gill, around more than 100 paper already written by Miss Professor Gill. From this curriculum vitae, Mr. Gill has experience teaching in STEM in United States. The title for this seminar is about reflecting on 10 years of STEM education reform in the United States. uh, Professor Jill will present STEM about how to teach STEM in United States. We have a little bit different between American and Indonesian. We call it a STEMI. In we call it a science, technology, engineering, management for Indonesian is a little bit different about STEM in and STEMI because in American I know I graduated from State University of Potsdam from my PhD in 1994. My professor was Professor Pribok, already died 2 years ago. In Indonesian, we have to come to the class about how to learn on STEM. But in an American, it'll be different. The teacher should stay in the lab in chemistry, and students come to the class. We call it in Indonesia a moving class, and we have to come to class, and the teacher should teach chemistry, and lab is a little bit different. It is a little bit different in Indonesia and then in American. Today, Professor Jill will has paper about reflecting often tenure of STEM in United States. In United States, a little bit different. STEM, they have funding from government about the STEM, but it's a little bit different in Indonesia. We have to make a proposal and research special in STEM. Because of STEM, I have a patent, one patent from government of Indonesia about how to titration for using a sensor and a little bit about a little about a program. Today, Professor Jill will bring a paper as will present about reflecting 10 years of STEM education reform in the United States. Okay, time is yours, Professor Jill.
Thank you
Okay.
very much for the kind introductions. It's a privilege to be able to talk to you all today. And I also hope that we'll have some future collaborations. I have Desi working with me again next year, which is exciting, and hopefully that will mean some continued partnerships. So let me get my slides up here. So it's good to start from the beginning. So let's get that ready. There we go. All right. Okay. So as our moderator mentioned, I'm going to talk a little bit today about some reflections on the past 10 years of STEM education reform in the United States, and some of the research that we've been doing. And hopefully you'll be able to see ways that it's similar or dissimilar to your context, and ways that might inform the work that you do in Indonesia. So I'll start off by talking about the current reforms in the United States. These reforms are guided by two main documents: the Framework for K-12 Science Education, which was released in 2012. This document ultimately led to the release of the Next Generation Science Standards, NGSS for short, in 2013. So that's where we're at, that sort of 10-year anniversary of the release of these documents. The NGSS reframes science teaching around what we call three-dimensional learning, which is what you see here on the graphic on the right. The three dimensions being disciplinary core ideas, practices, and cross-cutting concepts. The core ideas are the content that is going to be taught, so things like genetics, Newton's laws, etc. The practices are defined by 8 science and engineering practices, which include things such as modeling and argumentation. And we'll talk a little bit about those more as we go through the talk. And then students are expected to engage in these practices to learn the disciplinary core ideas. So these are not separate, these are integrated together. And finally, the third dimension is cross-cutting concepts, which are ways of thinking that are used across the science disciplines. For example, systems thinking would be one of the cross-cutting concepts. Now, when we look at these reforms in the United States is a little different from most countries in the world, including Indonesia. In the United States, we do not have a national curriculum. It is up to the individual states, all 50, to decide if and how they will follow the NGSS. This is a constantly changing map, but at this time, the states in dark blue have adopted NGSS as written. The states in gold used the 2012 framework to design their new science standards, and the states in light blue have chosen not to use the NGSS or the framework at all in how they think about teaching science. My state, Minnesota, right up here in the northern part, near the Canadian border, is one of the states that's heavily influenced by NGSS and the framework. So we don't adopt all of the NGSS, but we really are very much guided by it. It's important, though, as I talk about our work, that you know that in Minnesota, we integrated engineering standards into our science standards as early as 2009. So our work on integrated STEM actually has a longer history than the NGSS and a longer history than most of the states in the United States. So when we think about the frameworks and NGSS, the biggest change for our teachers from the previous policy and guideline was the addition of engineering being added both as a set of practices and as disciplinary core ideas. And just briefly, I want to share the rationale for including engineering into our science standards, and we'll come back to this and think about how this works throughout the talk as well. But the biggest argument is that engineering provides a real-world context for learning mathematics and science. So students have a purpose for learning. They know how that content is going to be applied. And then the other arguments are really around the development of problem solving and 21st century skills. So as students are working in real world contexts, coming up with possible solutions to real world problems, they have to engage in problem solving and 21st century skills. So unfortunately, as good as these frameworks are, they don't clearly define and operationalize STEM. And for schools and researchers, this means that we have a lot of different conceptions of STEM. And this can be problematic, and you'll see this play out throughout my talk. But something that almost all researchers and educators agree on is that the goals of STEM are intended to address the needs of the STEM workforce, to improve the STEM literacy of our general population and citizens, and to help students to address the grand challenges of the 21st century. The problem comes once you enter the classroom as a teacher or a researcher, that the word STEM can take on many different meanings. And I'm going to share 3 examples here with you just to show you some of the range of different conceptions that you might see. And this is coming from work by Roger Bybee that was done in around about 2008, 2010, as we were starting to think about the addition of engineering. So this is not my work here that I'm presenting on this slide. So the first image shows what we see most often in schools, is that even though we talk about STEM, schools are offering separate coursework in each of the STEM disciplines. So students go to science class, they go to mathematics class. They may go to technology or engineering classes. That is becoming more common, but not all schools offer technology or engineering classes. The second image shows the development that we see in some of our schools of elective courses that integrate 2 or more of the STEM disciplines. So, for example, we're seeing the growth of coding classes or computer science classes, and what we're seeing in those classes is the integration of science and technology. So bringing together some of the STEM disciplines in a new form of class, often around engineering or coding is where we see those things. And then the third example here is primarily what we do see with our science teachers and the work that we do in schools with science teachers. Because engineering has been put into the science standards. Our science standards are responsible for the teaching. And so what we see is science lessons where the teachers integrate technology, engineering, and mathematics when it's appropriate for the particular topic that they're teaching. And so it's a science class where the teacher is bringing in those connections to technology, engineering, and mathematics whenever possible. So there's a wide range of definitions of STEM, just like I've just shared some wide ranges of different implementations. And this is problematic. Over the past 10 years, there's been a focus on coming to consensus about the definitions of STEM. And what I'm sharing on the screen is one of the most widely cited definitions of STEM. This comes from Kelly and Knowles in 2016. And given the context of NGSS, I want to share with you how most often in the United States this definition is actually operationalized in classrooms. So when Kelly and Knowles say the approach to teaching STEM content of 2 or more of the STEM domains, most often what we see in the United States is that those 2 domains are science and engineering. Again, because our science teachers are the ones who are expected to do this integration work and the addition of engineering, and engineering because teachers are now expected to teach engineering. So it doesn't mean that technology and mathematics are not important, but those are the most common definitions that we see. The second part of their definition says that this integrated STEM work is bound by the STEM practices within an authentic context for the purpose of connecting these subjects to enhance student learning. Most often for us, again, because of this addition of engineering, we see that that authentic context and those STEM practices are very much guided by engineering design. And so you'll see a very heavy emphasis on engineering design in our work. All right, which may or may not fit well with the Indonesian context. So I just want you to bear that in mind as I talk through. So while the definition of Kelly and Knowles that I just shared is useful, we still need more detailed frameworks to help us as teachers and researchers to actually say, what is it that you want us to do in classrooms? What does integrated STEM look like? All Kelly and Knowles tell us is it's the integration of 2 or more of the content disciplines in an authentic context where students engage in STEM practices. We need to know a little bit more about that. And so this framework that I'm sharing here is some recent work from my research team. The QR code there in the corner is a link to the paper. So if you want to read about this framework in more detail, you can. It's an open access journal, so you should be able to readily access this paper. And so what we're arguing in this framework is that there are 7 characteristics of high quality integration represented on the screen here. So real world problem solving, engineering design challenges, context integration, content integration, STEM practices, 21st century skills, and STEM careers. I'm not going to go into detail with all of these. Again, you can access the paper if you want more details, but I will in the next few slides highlight a few of the critical pieces from this framework that really guide the work that we do in classrooms. So I'm going to start with STEM careers, and we'll spend a little bit of time on this slide. And the reason for this is that the STEM workforce is the primary driver for our STEM education reforms. We're really trying to address the growing demands on the STEM workforce. And the argument is really that integrated STEM curricula can help students to see connections to STEM careers and motivate students to STEM careers. And what we hope to see in our classrooms and in our curriculum is that these STEM careers are explicitly included and discussed, and also that students implicitly connect to STEM careers and are able to engage in some of the practices that engineers and scientists would engage in. So the graphic there on the bottom, I'd like to take a deeper look at this and think about what do we mean when we say we're addressing STEM workforce problems, and what is it exactly that we want the reforms to do. And so the image here refers to what we call the STEM pipeline problem. And you can see that there are leaks in this pipeline. And so I'll walk you through the numbers here. So the numbers that I have are from the state of California. So each year in California, approximately 4 million students enter high school. Of those 4 million students, as they go through 4 years in high school, only 1.3 million graduate college ready. So they've taken high enough levels of coursework etc., to be ready to go to college. So we've got attrition in the pipeline already. As we think about those 1.3 million students, only 278,000 of them choose STEM as their degree path. So it could be biology, could be chemistry, could be engineering, etc. And unfortunately, of those, not all of them complete their degree. Some of them drop out. Some of them may change their major and do a non-STEM degree. So ultimately, from those 4 million students who enter high school, only 167,000 of them actually graduate with a 4-year STEM degree. So that's about 4%. It's a really low number. And so we want to get more students successfully working through this pipeline with an interest in STEM and completing STEM degrees. What our research shows us is that these leaks in the pipeline, while some of them are due to achievement and ability, the biggest issue that we face is lack of interest in STEM. And that's the reason that so many of our students are actually leaking from the pipeline. The other thing that we focus in our work is the fact that these leaks from the pipeline are not the same for all students. So I'll just share a couple of examples to illustrate that. When we look at who is out here, right, this 167,000 people who graduate with a STEM degree who maybe go into the workforce, only 12% of our engineers in the US are female. So we can tell that our female students are exiting the STEM pipeline at a far more higher rate than our male students. Also, when we look, we're a very diverse country in the United States. When we look at our STEM workforce, 87% of our STEM workforce is white, compared to about 60% of our total population. So our non-white students are also exiting the pipeline at far greater rates than our other students. So we really try to attend to that in our work that we do. And so some of that we look at in terms of how we represent real world problems. So as I mentioned on an earlier slide, the idea here is that these real world problems are motivating and engaging for students. They can understand how they might use chemistry knowledge in their future lives. But we have to think really carefully about the kinds of problems and engineering design challenges that we use. And I'll just use gender to illustrate this. And I'm going to look at a technical orientation to how we teach STEM versus a communal orientation as to how we teach STEM. And this really matters in terms of gender and keeping students in the pipeline. Oh, there we go. So when we think about a technical orientation, these are the kinds of curricula and the kinds of problems that appeal to our male students. Things like making faster cars, faster rockets, taller buildings. And unfortunately, these are the most common curricular activities that we see. We see curriculum where students are building mousetrap cars, bottle rockets, toothpick bridges, things like that. However, for our female students, these are not as motivating. Female students tend to have what we refer to as a communal orientation. And what this means is that our female students are motivated by how a topic or a career can help people and communities and the world. So our female students are far more likely to gravitate to topics and careers that involve things such as health, alternative energy, the environment, and sustainability, that have that sense that the work that they do could save people's lives, it could improve a community's health and well-being, things like that. And it's not that these jobs don't require technical knowledge, right? Anyone who works in the solar industry needs technical knowledge, but it's that focus on empathy and caring that helps to keep more female students engaged and motivated and interested in STEM. So as we think about our STEM problems, we have to think really carefully about the orientation that we're representing and the ultimate what a STEM career might look like to those students. I can only talk about this one briefly. It will come up throughout other slides, but in many ways, this is one of the most important pieces around STEM integration, and the piece that we work the hardest with our curriculum on is it's really important that the real world problem or engineering design challenge should require the application of STEM content. We want students to learn and apply, be it chemistry content, mathematics content, biology content, to learn that content and then use that content to be able to develop solutions to real world problems. If we don't do that, we just end up with curriculum that's a craft project. We build something, but we don't actually use science in building it. So that's not going to say much here, but I'll have some examples later on. Actually, I have an example right now. There we go. I forgot what was on my next slide. So this is an example from a STEM activity that we've done with students as young as 6th grade. We've done it with high school students. We've actually done this with college students as well. The students are asked to build a prototype for a habitat to protect penguins in South Africa. And the problem faced by these penguins is rapidly rising temperatures because of climate change. And the penguins need a safe, a cool place to be able to hatch their eggs. And so the students do some design work about how could we build a habitat to help keep the penguins cool. So the students learn concepts related to heat transfer. They learn topics such as insulation, convection, conduction, and radiation. And then the students are asked to apply these concepts to design their prototype habitats. And what I have on the screen here is an example of a habitat the students have designed to try and help keep a penguin cool, right? And so you can see a variety of things that the students have done here. And what we ask the students to do is to explicitly talk about how they use their content knowledge to make their design decisions. So for example, this group of students has chosen to use mylar, which is a very shiny material. And their explanation for using mylar is that it helps to reflect the radiation from the sun. So it's slowing down heat transfer by radiation. They've also used insulation. You can see some sort of cotton wool kind of material here. And their explanation for that, they're applying their ideas about what makes a good insulating material and how by insulating this habitat, they can slow down heat transfer. A third thing here that you may see in their design is they're saying if we're able to lift this habitat off of the hot sands just a little bit, that means that the habitat is not touching the hot sand, and that will help to prevent heat transfer by conduction. So what we see in this curriculum is that students need to understand heat transfer to be able to make good design decisions, and that when our students explain their designs, we see their understanding of that heat transfer content. The next two that I'll just touch on briefly are STEM practices and 21st century skills. So the whole idea here is that students are engaging in the same kinds of practices that scientists and engineers do. You could see in the penguins example, right, students are asking questions, they're planning and carrying out investigations, they're developing models for how they might build a habitat, those kinds of things. So these science and engineering practices are evident as students work through the curriculum. It's also important that as we think about that the students have agency in making these design decisions. We cannot do integrated STEM by providing a set of directions for students and telling them first do this, next do this, third do this. We have to give the students agency and allow them the space to decide how they might design these solutions. They may make mistakes. That's okay. Students can learn from those mistakes as well. In terms of STEM practices, right, so we specifically look here at critical thinking, creativity, collaboration, and communication. And what we look here is the idea is that these real world problems are complex and there are multiple possible solutions. So when we think about the penguin habitat, there are many ways you could design a habitat to keep a penguin cool. Right? So this requires some creativity from the students. If you have multiple possible solutions, you have to make decisions about which is better and why is it better. That involves critical thinking. And again, as I mentioned on the previous slide, in terms of agency, students are going to make mistakes. Engineers make mistakes, right? When my brother, my husband, both work as engineers, the first designs they make, the second designs they make often don't work properly. Engineers learn from those mistakes. They generate new knowledge from those mistakes and they innovate from those failures. So learning from failure is a really critical piece of this integrated STEM, and it's what helps to elevate those 21st century skills. So given the framework that we use for integrated STEM and our focus in the United States of bringing engineering into the K-12 space, our curricular approach is centered around the engineering design process. You will find many, many models of the engineering design process in the literature. I've just put a couple of examples here on my slide. But there are some common features. So all engineering design cycles start with defining a problem, understanding what is the problem, what does the client want, and making sure that we understand that. Once we understand the problem, all engineers go into a process where they have to do some research. They have to learn new knowledge to decide how they are going to address that problem. All engineers then go into this iterative space where they prototype something, they test it, they use that data to improve it, they test it again, they use that data to improve it. So they iteratively go through this design and redesign cycle. And so ultimately, they have a product that they are ready to share, a possible design solution for the client. So what I'll do in the next few slides is I'll share a curriculum and I'll show you how we anchor that to our engineering design process. And the curriculum example that I'll share, this is a middle school curriculum, and it's a physics curriculum, so physics for 6th grade students. And so we start with the problem, right? So in the problem phase, the students are being asked to understand who is our client, what does the client need, and what are any criteria and constraints that we need to consider as we think about designing possible solutions. In this example, the students are introduced to the client, which is a company called Galactic Games. And Galactic Games are asking the students to help them with a problem that they have. And what you see on the right side of the screen here, might be your left, I'm thinking as we're reorienting the screen as you're watching, is a common game that students play, particularly when they're young. You put your quarter in the machine, you move this arm, and you try and grab the toy that you want, and hopefully your hope is to win one of those toys. And what Galactic Games are asking is for the students to design a new arm instead of a mechanical arm. They would like an electromagnetic arm that they believe will be more reliable and will improve the experience with this game. So once the students understand what the client needs, they understand what the problem that they're going to be working with, the second phase of our curriculum, we move to what we call the learn phase. And in the learn phase, the students are going to learn the necessary background knowledge, anything they need to know about the materials that they're going to be using. So in this curriculum, there's a series of science lessons where students are going to learn about magnets and electromagnetism. They engage in some inquiry experiments where they explore the different variables that will impact the strength of an electromagnet. So for example, they explore the number of coils of wire. They might explore the gauge or the thickness of that wire. They may investigate what happens if they use more batteries or different kinds of batteries. They can also investigate what we use as the core of the electromagnet. So they investigate those in an inquiry manner, understanding how those different variables impact how many we use paper clips, right, that they're able to pick up. So as they exit the learn phase, they have a really strong understanding of electromagnets and how electromagnetism works. We then move on to the plan phase. And during the plan phase, we ask students to come up with possible designs for their clients, Galactic Games. And to promote creativity and critical thinking, we ask our students to do several brainstorming processes. We first ask them individually to write down 3 possible designs, 3 different designs that could work. They then work collaboratively in their group, communicating their different ideas. And from all of the ideas that they have, they work to come to consensus on what their first design that they're going to test is. And we ask them to plan this out and draw it out on paper before they build the actual physical electromagnet. The students then move into this iterative try-test phase, right? So in try, they're going to take their plan, they're going to build their electromagnet, they're going to test it, they're going to analyze their test data and come up with ways that they could improve the design. They're going to rebuild an improved prototype, test it again, and they're going to go through several iterations to improve the design of their electromagnet. And you can see a group of 4 of the girls there working in that process in one of our classrooms. Finally, at the end of this, students have to decide on a final solution, right? The curriculum has to end. And we ask them to then write up and present that solution to the client. And this happens in a variety of different ways. Students could be communicating through a written report or a letter. They could be doing a presentation to the clients. But one of the things we ask them, whether it's a verbal or a written report, is that they include in their report to the client their data and their justifications for their design decisions. So you can see a snapshot there on the screen of what that might look like. The students are saying, what kind of batteries did we decide to use and why did we choose those batteries, etc. So we're making sure, again, that the students are showing us that they understand the science content and that they're using the science content to come up with a good design for the client. So I'm going to switch gears a little bit here, talked a little bit about a curriculum example and a little bit about our framework. But I want to talk a little bit as well about some of the research that we've been doing. And so when we started to engage in this work 10 years ago, and we've done a lot of work in the last 10 years, one of the problems that we had is that we had no existing observation instrument that would allow us to go into classrooms and make observations and actually measure or assess the quality of integrated STEM instruction. Our early work, we had to rely on existing observation protocols that are in the literature. I've just shared a few there. They're excellent protocols. The problem is they were designed for the previous standards and they focus on science instruction, not integrated STEM instruction. And so we tried using the Reform Teaching Observation Protocol, and we just found that it was not sensitive and not measuring some of the critical, important parts of integrated STEM. And so with our research team, we submitted a proposal to the National Science Foundation and said, we would like some research funding to develop a new protocol that we will then share and disseminate for others to use. And so that work was funded 4 years ago. And so again, the goal was for our team to establish a valid and reliable instrument that would be able to identify and describe high quality STEM teaching in K-12 classrooms. And I just want to make sure that I acknowledge my research team here. This is not me working by myself by any stretch of the imagination. So I want to make sure that I acknowledge Doctors Emily Dare and Joshua Ellis, who are from Florida International University, and Dr. Elizabeth Ring, who is from St. Catherine University, which is another university in Minnesota, and also our project statistician, Dr. Mark Rulo, who is from Michigan Tech. And also there are many graduate students and postdoctoral scholars who've worked on this as well. And so we're now entering, just about to complete our 4th year of the project, and we have developed a STEM protocol. I'm going to share that with you and talked about, and if anyone is interested in this, I'm happy to share the protocol, send you a link if you find it useful to use with your teachers or in your research. I won't talk a lot about the development of the instrument, just really briefly so you can understand our process. This QR code that I have here is to a different paper. It's also open access, so you should be able to access this without any problems. And that paper talks in a lot of detail about our instrument design process. So if any of you do that kind of work and you're interested in the details, you'll find them there. So just briefly, so you know how we grounded this instrument. So we drew on the framework that I shared with you, those 7 characteristics of integrated STEM. But we were also lucky to have access to a video inventory of over 2,000 K-12 integrated STEM classroom videos from a previous project. And so we investigated a small number of those. We brainstormed possible items. We actually came up with 70 items at the beginning, which was kind of crazy. We looked at grouping those into different domains, ones that looked at student learning, lesson implementation, and teaching approaches. We kept going back to the literature. We kept iterating, going through discussions, and as we analyzed and consolidated these items. We ended up, as we came close to the end of this process, with an instrument that had 13 items, and we had levels for those items as 0, 1, 2, and 3. We continued then to do more detailed testing around inter-rater reliability. So we actually scored about 70 videos. There was a team of 6 of us, myself and 5 graduate students who did that scoring to see, were we able to consistently use and score these items. And ultimately through that IRR process and also talking with our external advisory board, our final instrument contains 10 items, each of 4 different levels. All right. And so what I'll share on the next slide is so you can see what those 10 items are. And I'll share an example of one of the items on the next slide as well. So you can see the 10 items there, anything from relating content to students' lives, contextualizing content, cognitive engagement, evidence-based reasoning, technology practices, connections to STEM careers, etc. So those are our 10 items. We have a document, again, that I'm happy to share with you that has brief descriptions of these. It talks about the items and also a set of user guidelines. But so you can get a sense as to what this entails. I'm just going to share one of the items here in detail so you can get a sense as to what an item would look like. So this is item 3, and this item focuses on developing multiple solutions. So what we're hoping here that we see in teachers' classrooms is that the teacher is allowing the student the opportunity to develop multiple design solutions to a real world problem, that they're able to evaluate, sort through those problems, improve them, and ultimately suggest a solution to the client. So as we go into a classroom and we observe, if we don't see any evidence that the teacher is encouraging in the development of multiple solutions, the lesson simply scores a 0. It doesn't mean it's a bad lesson necessarily. It just means we didn't see any evidence of this particular item. At a level 1, we would observe the teacher allowing the students to develop multiple possible solutions. They might be brainstorming ideas for their electromagnetic crane arm, but we don't see the students evaluating or testing those ideas. At level 2, we would see the students going on to the next phase, so they have multiple possible solutions, and the teacher is now engaging the students with evaluating those different solutions and starting to pick between those different solutions. And finally, at the highest level, level 3, the students would not only be evaluating the different designs, but they would be iteratively improving their designs and moving forward different possible design solutions through that iterative improvement process. All right, so all of the items have this same structure with the 0 through 3. I'll talk about a few more of the items throughout the talk, but it will take us way too long to go through all of the items individually. So our next step, and this is where I want to spend a little bit of time because I want you to see how these items play out and what are some of the big dimensions of STEM, is we needed to move on to some of that statistical work that we need to do with instrument development. And so we wanted to explore the dimensionality of our STEM protocol, and so we used principal component analysis using our full video inventory. When I say full video inventory, I mean that we scored all 2,030 videos. So between myself and the graduate students, we scored all of these. And just to give you a sense where these videos come from, so you've got a sense of the data that we used. These were all from teachers who had participated in an intensive professional development project. They had worked as teams to develop integrated STEM curriculum from that PD. One of them was that electromagnetic crane arm example that I shared on the previous slides, actually. And the teachers then implemented these curriculum in their classrooms, and the research team videotaped every single lesson of these units, which is where those 2,300 videos came from. You can see there on the other side of the screen just a breakdown as to the split between physical science content, earth science content, and life science content, and also the grade levels that these videos occurred at. You can see that we've got a lot of elementary and middle school classrooms that we worked with, not many high schools. This was one of the problems we had with COVID, unfortunately, with this project. Part of what we were hoping to do is to go into more high school classrooms and collect more video. We were not able to do that because of the pandemic. So one of the things we would like to do with some of our future research is to look more heavily into high school classrooms and make sure that the instrument is truly reliable in that space, not just elementary and middle school spaces. So I've got 3 slides here where I'm going to share some of our different PCA analysis. Any of you who do statistical analysis, we're looking at different ways of going about the PCA. So for example, using a Promax rotation or not using a rotation in our data. So some different statistical details with how we did that. But what I want you to focus on is the commonalities as we go through those. So in this first analysis, you can see that that we have 3 dimensions of STEM in our protocol. So we've got component 1, where we see items 3, 4, 6, 7, and 8 grouping together here. Component 2, where you see 1, 2, 5, and 10. And then you can see this sort of mysterious component 3, where we've actually got some negative loading on here going on. As I flip to the next one, what you'll see, actually, I flipped the slide too quickly here. So as we go from the first analysis to the second, there's some things in common here. If you look at component 1, the only change here is the loading now of item 2. All right, so similar loading, item 2 is now loading into component 1. Component 2, as I go from one analysis to the next, is identical. Items 1, 2, 5, and 10. We're now seeing some changes again in component 3. So component 3 is not very stable. And in our final PCA analysis, this was without reporting without the rotation, we're now seeing, again, those stable 2 components. So we see component 1 with that set of items, and I'll talk about that in a little bit more detail on the next slide. We see component 2 with that consistent loading of those items, and component 3 has now disappeared, right? You could see the variation there and the lack of stability. So one thing I will note before I go to the next slide here is you see that item 9 is not loading at all in this analysis, and item 9 floats around in different places. It loads in this mysterious unstable third item in these other analyses. Item 9, just to briefly mention it, particularly because our moderator mentioned his patent to do with coding. Item 9 is around technology practices. And we did not see a heavy use of technology practices in the classrooms that we observed. So one of the things we'd really like to explore in the future is work with teachers more around technology practices, and hopefully actually see more classrooms with this happening. So item 9 was not observed very, very often, unfortunately, and so it's not surprising to us that it doesn't load well in the instrument. So we definitely have some work there to do with our teachers and also around then our instrument as well. But these 2 dimensions that we have, we feel really confident about what these look like. And so I'm just going to briefly talk about those. The first we call real world problem solving. And you can see now I put it so it's not just the items, you can see which the titles of the items actually load. So within real world problem solving, I'll just talk about a few of these, how they connect. So we see 6 items that are loading. Item 2 was the one that only loaded in 2 of the 3 analyses, but that inclusion of item 2 really aligns strongly with our framework for integrated STEM. One of our arguments is that integrated STEM has to occur around a real world problem that students engage with. So it makes sense to us if you're doing real world problem solving, you have to have a real world problem to contextualize learning. So the presence of item 2 really makes sense to us here. And given that we have a real world problem that students are engaging with, we know that as students engage with that real world problem, they're going to need to develop and evaluate possible design solutions to that problem. So we're not surprised here to see the presence of item 3. We talked earlier about the importance of students' agency. So students are doing this work. Students are actively engaged in coming up with their own design decisions. So item 6 that you see here in this dimension. One of the important STEM practices here when you're working with real world problems is that you use evidence-based reasoning. So you're taking that knowledge that you have of chemistry or mathematics or even economics maybe, and you're using that knowledge to help with those design solutions. So that's what item 8 is all about, that utilization of content knowledge to do real world problem solving. It's also notable, item 4 loads highly into this item, and that's the levels of cognitive thinking that students have to engage in. So what we're seeing is that as students engage in these integrated STEM lessons, they need to do those higher cognitive, higher Bloom's kinds of thinking. So they're evaluating and analyzing, not just remembering facts and content. And a lot of this work happens in teams as we observe these classrooms. Students are often in small groups. They're engaged in collaboratively coming up with design solutions. And that's where we see the loading of item 7. All right. So these are the important characteristics of how students should engage in classrooms with real world problem solving. So that's our first dimension. Our second dimension we call the nature of STEM integration. And this is looking at the different ways in which integration can and should occur across a curriculum. And so the same 4 items were consistently loading throughout our PCA analysis. And I'll just touch on the different ways that we see integration happening, and that these should be happening, what this item is telling us, in conjunction with each other, is what this dimension is telling us. So item 1 says that we need to be relating content to students' lives and everyday experiences. So they have that connection to their actual lives and understanding. And the second one we've talked about a lot. I can't emphasize enough that that's like central to integrated STEM, right? That there's a real world problem that contextualizes all of the learning, and the students are going to apply the knowledge they're learning to that problem. Item 5 is really tricky, but that's that integration across the STEM content disciplines. So how do students bring their knowledge of mathematics and their knowledge of science together, for example? or their knowledge of engineering and technology together with their knowledge of science. It's integrating across the content domains. And I know as some of you engage more with Desi, as she's back with you for a few weeks, that for one example would be the work that she does. I was really looking heavily as how we integrate mathematical learning and science learning together would be one example of that. And then finally, the last way that this dimension works and ways that we want to see this integration happening is that connection to STEM careers. STEM careers provide a way to contextualize learning, and students can understand how the content that they're learning is going to be applied and used in the real world in terms of specific careers. All right, I've talked a lot about integrated STEM. I know a lot of you are chemistry people, right? You're all from the department of chemistry education and things like that. So I wanted to make sure that I did end by talking a little bit about chemistry and provide a chemistry example for you. I want to make a couple of things really clear about this that I haven't said in my slides up to this point, and is that not all topics lend themselves to integrated STEM. We do not ask and we do not expect our teachers to use integrated STEM all of the time. Honestly, it would be crazy, right? You can't connect every topic that you teach to real world problems. So for example, thinking about when I taught high school chemistry and I taught high school at San Diego State before moving to Minnesota, there's some topics that I would teach, like naming chemical compounds, ionic and covalent bonding. Those are things that I use basic disciplinary approaches. They're fundamental chemistry concepts, and they're not necessarily well suited to contextualizing with real world problems. So there are many topics that you will continue to teach in ways that don't use integrated STEM. So I just want to make that really clear. We're not advocating integrated STEM all of the time, right? And part of that is the second bullet that I have here, which is particularly as chemistry teachers, we have to think about safety, we have to think about cost, and we also have to think about time. I think all teachers have to think about time, right? How much time do we have on a certain topic? Because you can already see from some of the examples that I've shared, it takes a little bit longer to do an integrated STEM approach than a more traditional approach to teaching content. But particularly for us as chemists, we've got to think about safety, right? What chemicals students might be using, and if we're going to give them agency, what is safe for them to mix together or not to mix together. So we have some things we really have to think carefully about. And I'll try and highlight those a little bit in the example that I'm going to share. And so the example I'm going to share, I just want to acknowledge again where this is coming from. I actually just wrapped up this morning a class with our pre-service teachers. They were doing their presentations this week, and this example comes from one of their curriculum that they shared with me this week. And some of the students took a green chemistry workshop that was run by our Center for Sustainable Polymers, and they took some ideas from that green chemistry workshop and they developed them into the integrated STEM curriculum. That was their final project for my class. So I just want to acknowledge again, this is not my idea. This is, my students are way more brilliant at this than I am. So this focuses on polymers, right, which is a pretty common content that we teach as we think about organic chemistry and different things like that. It's a very accessible content actually to students when they're thinking about bonding and different things. And we're looking at it in the specific form. There are many kinds of polymers, right, but we're specifically looking at plastics here. And what becomes interesting is plastics, when we think about real world problems, is that plastics provide solutions to problems. You can see some there on the screen, right? They help us to design cell phones, water bottles, plastic bags, shoes, all sorts of things, right? Human problems that they're helping to solve. But they also come at a cost, right? Some of these products cause all sorts of problems that we have to think about in terms of the real world. And I've just put a couple there. So for example, that image on the bottom is the Great Pacific Garbage Patch, right? So all of these plastic water bottles and plastic bags that we have do not degrade, right? They get thrown away, they end up in the water, and they're just sitting there. It will be centuries before they break down, if they break down, all right? And so what the students brought forward from this, right, thinking about item 2 from the STEM up, we've got all sorts of ways we can contextualize learning, right? And think about what are problems that we have with our use of plastics and how might we use chemistry to help solve and improve some of those problems. And so the specific problem that the student engaged in was our overuse of plastic water bottles, right? And how they're now sitting in the Pacific garbage patch, and how can we come up with alternatives to our use of plastic water bottles. And they used a specific problem, which was around, they tested this product at the London Marathon. And so if you've ever been, I am not a runner, I don't know if any of you are, but if you've ever run in a marathon or if you've seen one, there are constantly people on the sideline who are handing out water bottles. So the marathon runners, they take a drink, they pour it over their head, and they throw that plastic water bottle away. And so what this company did is they developed what they call a hydrogel capsule, and you can see it there that is being held in a person's hand there. And this is made out of a biodegradable polymer. And they handed these out. You can see on the other picture, right, the staff person is holding it out. The runner can grab this. Because it's a biodegradable polymer, the runner can just put it in their mouth and they can eat the whole thing. There's no waste. The plastic is able to be eaten. There's no plastic water bottles. So you can imagine all sorts of other extensions that could come from this. And so what the students then engage in is a series of investigations around these green chemistry solutions and creating sustainable polymers. And in this particular one, I'm not going to go over all of the chemistry here, but just there's enough here on the screen to sort of tease your chemistry minds here a little bit, is the students are reacting a lactate salt with sodium alginate, and that is helping to create a new gel. And it's that ion that is helping to provide the cross-linking between the polymer chains. And students are able to explore this reaction. They can try different lactate salts. It does have to be a group 2 metal ion there, but they can try magnesium, they can try strontium, etc. There's different ones that they can try and look at how that might change the properties of the hydrogel. One of the things, obviously, that they have to think about, if you just think about my last slide, that person is eating it, it would be a really bad idea to use strontium, right? Strontium may improve the but again, right, we have constraints we have to think about. Strontium would be a really bad idea to put into your mouth. Another thing they can investigate is manipulating the pH of this reaction. This reaction is pH sensitive, so there's a variety of variables that they can moderate to some degree and look at how it may improve the design of their capsule. The pH actually becomes really interesting when you think about the contents of the capsule. So if I'm going to have a water capsule that someone can grab and consume, right? Instead of their plastic water bottle, I don't really have to worry too much about pH. It's neutral. But as the pH gets too low, these polymers degrade, and the hydrogel will start to break up. So if you want to have let's say apple juice or Gatorade in these capsules, you have to rethink how you design that sustainable polymer because of the pH of the content. There are ways to do that, but you have to manipulate the chemistry, re-engineer that hydrogel. So there's a whole variety of ways that students can engage in this. They have an opportunity to have some level of agency, right, in terms of trying different concentrations, different pHs here to see how those variables change things. So there's some agency while maintaining some safety protocols in here. So they are able to come up with a variety of design solutions, which addresses item 3. A lot of engaging in evidence-based reasoning, which was item 8, right? So saying, yes, strontium works great. We actually get a stronger gel. It's stronger in terms of containing the liquid. However, you can't consume strontium, right? So there's some evidence-based reasoning that students are able to engage in there. So I just wanted to give you sort of a quick taste of what that could look like in a chemistry space. Got other examples I could share, but this was one that I just loved, this example that this curriculum students shared with me earlier this week. All right, I'm going to wrap up with some acknowledgements again, because I always want to make sure that it's clear who was responsible for this work and where the funding came from, and then I'll give a chance to answer questions. So I just want to formally acknowledge the National Science Foundation, who've supported this work, both for the project that created the video inventory set that we used and the work that was used to develop the STEM Up instrument. I want to acknowledge my collaborators again, because the STEM Up instrument would not have happened without the work of Drs. Emily Dare, Joshua Ellis, Elizabeth Ring-Whalen, and Dr. Mark Rulo, as well as the many graduate students who've been part of the project. I want to acknowledge the Center for Sustainable Polymers, and those green chemistry connections I just shared, they have an amazing set of different. I just shared one there of experiments that I would be happy to share with you that you could use to do some integrated work in chemistry. So I'll stop there. I've got my email on the screen. I'm happy to answer any questions you have at this time. I'm also happy if you have questions later and you would like to email me, or if you'd like copies of any papers, those kinds of things, please feel free to email me. So I'm going to stop sharing my screen here so I can see you all. Okay. And happy to take any questions that we have from the audience.
Yes, before the audience has a question, I have a question for Jill. Is 12% is including Daisy or not?
I'm sorry, ask me again.
12% is in our women's. It is including Daisy or not?
So yeah, 12. That data is about. Does it include Desi? so the 12% is from working engineers. Okay. So it's not 12% of people who have an engineering degree. If it was people who have an engineering degree, Desi would be included, right? The 12% is people who actually work, so professional engineers. Okay. So Desi would not be part of the 12%.
Okay. And the second question is, it is possible in the United States has a STEM in high school level. You have a university level in STEM, Department of STEM in University of Utah. But it is possible STEM in high school level because all your video is high school, middle school, and elementary school. It is possible because in Indonesia has like electrical, civil, and mechanic in high school level. We call it vocational school here in Indonesia. But in United, it is possible for the next future has a STEM in level of high school level.
It's definitely possible in high school. The problem we had with the video was simply the previous project. We worked only almost exclusively with elementary, middle school teachers. So the reason we have less high school video is not because high school teachers are not doing STEM. It was just the access to the data that we had. What I will say is we see our high school teachers struggle more to do integrated STEM than our elementary and our middle school teachers. And I think some of this has to do, and I've seen this in other countries too. I'm working on a paper with a colleague in Egypt right now. And at the high school level, we get so focused on passing our exams to go to university, right? And you need to pass your chemistry test, you need to pass your math test, all of these different things, that we tend to go back to these traditional disciplinary spaces, and we have this traditional idea of college entrance exams. That creates a tension for our high school teachers. They struggle a little bit, but some of them do it really well. And we have some classes. One of the teachers that I worked with in the class we just finished, she teaches a biomedical engineering class at high school, for example. So it's definitely possible. We just see more struggle with our high school teachers doing this kind of work.
Yes, we don't have here in Indonesia about the STEM department like we do have in American, and for university has a STEM department, but here we don't have it STEM problem even in university. As far as I know, in American, I used to live in United States for 7 years in New York State. So I know that vocational school for STEM is we don't have it in Indonesia or even in American.
Everywhere in the United States has a STEM professional school. And so really the work we do, I mean, we have a STEM program, which is really nice for the work that I do. But what we try and highlight in our work, so for example, the example with the polymers, that's taught by a chemistry teacher, right? That's a high school chemistry teacher who does that. They're not a STEM person. They don't have to be in a STEM school. So what we would like to see is that whether you're a biology teacher, you're a chemistry teacher, a physics teacher, whatever you might teach, there are ways to do integrated STEM while you teach that discipline, right? So that it doesn't have to be a STEM school. It can also happen in a chemistry department, in a biology department, right?
Yes, STEM is like we do have we hear in Indonesian about the STEM. Even in our department, they don't have STEM. I already researched STEM since in 2013, but government has started like 2 years ago about STEM problem.
Right.
I think I already we already sent Desi in United States about STEM.
Right. And we I don't think we want to send her back to you. We love having Desi with us.
Okay.
We've got other. We also, I mean, so Desi is one of our students from Indonesia. I've got a couple of other students from Indonesia as well that have just started. They've only been with me for a year. So there's a very large interest in STEM from Indonesia, definitely. So.
Okay. It is possible for the next future student in Indonesia study STEM in American. In your department.
We're happy to have we actually have a fourth student. I haven't met him yet. So we have a teacher from Indonesia working in our pre-service teacher program. He already teaches physics in Indonesia, and I don't remember where he's from. So but he's here to learn in our pre-service program how to teach integrated STEM and bring that work back to Indonesia. So we're seeing both teachers and researchers coming to us.
School, TOEFL also in United States.
I'm sorry, say that again.
In your school, still have TOEFL requirement for student STEM, or we can send it from our department study about STEM.
Right. We have students who come in from all sorts of different spaces. So yeah.
Okay. The audience, is there any question about STEM? To Jill, Professor Jill Rohik. I know your name is from England, right?
My first name is from England. My last name is actually German. My husband is German.
Oh, German. Okay.
So yeah, his family is German. So
okay. Yeah, mostly most our teacher, lecturer from Europe. Freiburg from Swiss, mostly from Europe, not from England or German. Is there any question? Okay. The one question, Jill, Professor Jill from student. Okay.
Hello, Professor Jill. I'm Surya
Hello.
Dewi from Sriwijaya University in Chemistry Education. STEM encourages students to have creativity, critical thinking, and communication, and more. But a way to have high creativity, critical thinking, and good communication is to have a practice, like how to solve STEM problems. But in fact, and I remember my lecturer in Sriwijaya University and my teacher in my senior high school told me that practice make perfect. But in fact, not all students understand the method or problems given. Meanwhile, to hone creativity and critical thinking, so high-order thinking skills are needed. If students cannot solve problems well, they will get bad grades. Teachers also want their students to get good grades. So the teacher give exercises or questions. The teacher gives easy problems so that students get good grades, but low creativity and critical thinking to solve STEM problems or gives difficult problems that students' creativity and critical thinking are trained but get bad grades. Thank you.
It's I'm still smiling with practice makes perfect. Practice may make perfect with some things, right? I can practice my golf swing, I can practice certain skills, and I can get better at them, right? I'd say in engineering and in real world problems, practice makes better, but practice doesn't make perfect, right? So anything we engineer in the real world, we can always improve it, right? Make it more sustainable. So I'm going to have to think about practice makes perfect. That's not true in STEM necessarily. So one of the things we really work with STEM around the idea with creativity and innovation is that we have to change the mindset of our students and our parents, right? That as to what it means to be successful, right? So when I went to school, memorizing, getting good grades, right? Those were, it was important to be able to memorize. I didn't have the internet, right? I didn't have a device that I could Google and look things up, right? So the kinds of skills I needed were different, right? But for our students, the memorizing is irrelevant. I can Google anything, right? What we need if we're going to survive, right, as a human race, is we have to be able to innovate. We have to be able to solve some of these problems. And you can't do that in the traditional ways that we teach schools. So we have to start to slowly shift. If we shift too much, it's going to upset things. So just those small changes, right? So maybe you just add like one integrated STEM a semester to start with, to give students just some experience with developing these kinds of ideas. If you talk to people, to companies, businesses, when they hire people, what they look for is those critical thinking skills, those 21st century skills. They are looking for someone who can collaborate, someone who can innovate, right? Because that company needs that to be successful. So it's really trying to slowly change the mindset of what school means for our students. What we found with our students is they are able to engage in this. They are okay to fail, okay to try again. They are fairly comfortable in this space. It's the parents who are not comfortable, right? They want to see the scores on those exams. So trying to balance that is very, very difficult.
Okay. Is there any question? The question is offered to the audience from the what is you call it, from the online Zil. Professor Jill, the question is not from the audience who has the meeting right now, but from the Zoom online. Is there any question from the Zoom online to the Zeal? Just not from the audience in this meeting, but online.
I don't see anything in the chats.
Oh, okay.
I see a couple of things, but they're links to some forms.
Okay. Is there any question from the online to Professor Jill?
I'm sure if you want to ask your question in Indonesian, I don't speak a word of Indonesian, but I'm sure our moderator or Desi or others can help translate that. I know it can be very intimidating and difficult to ask the question in English, so maybe we can open that up. I see that someone's raised their hand. Dewey, am I saying that correctly?
Jill, there is a raised hand in online. Maybe
yes.
They have a question. Okay.
Yes.
Okay.
Let's see.
Oh, maybe they have a
change their mind. Yes. That's okay.
Okay. Okay. Pak Rodi has a question from this meeting. Okay.
Okay.
Good evening, Jill.
Good evening.
I apologize if my question little bit different from the topic. First of all, I would like to say thank you for this opportunity, for this moment. And I want to introduce myself. My name is Rodi Edi. I'm from Chemistry Education, Sriwijaya University. Yeah, I'm a lecturer. I want to ask you regarding to the topic, especially when we talk about teaching and learning process. As we know, almost all teaching and learning process nowadays organized by online process. And I think it is the critical thing that I want to ask you. Yeah. It is possible to use them in teaching and learning process based on online process, or how to apply the STEM approach when we learn online. Thank you.
It's a great question. I've actually taught my last 3 STEM classes online, so I've lived that experience. The class I was talking about with the student presentations from this week is also online. There are ways you can teach STEM online, definitely. You have to pick carefully the kinds of problems you do, right? So my sustainable polymer example would not work really well online, right? That the students aren't able to do that. But there are some things that you can do where students can use materials that they have in their house, things like paper, straws, things like that. We've done some teaching, particularly during the pandemic, where we actually created STEM kits that we mailed to students' houses. So they were able to work on Zoom together, and they had the materials that we'd sent home to them. So it could be batteries and wires, things like that. So fairly cheap materials that that they could use safely at their kitchen. So there's many ways that we can do that. What I found is every way that we've done it online, we've had to come up with ways that students can still use materials. So whether it's something in their kitchen or something we mail to them, that use of manipulation of materials has been pretty critical to us, and that's made it difficult to teach online. There are some simulations that I've seen online that I think could work pretty well. There are ways you can design electromagnets, for example, online by manipulating a simulation. So I think as we develop more tools like that, I think we will be able to expand what we can do online. But it definitely makes it more difficult to do that. That's for sure. But it's possible. I think for those of you who teach chemistry, it's just even harder. There are only so many things, right, that are safe that you can do in terms of chemistry, where students aren't in the lab and not working with you face to face. I think it just makes it really difficult.
Okay. Is there any question instead of Rodi Edi to Professor Sil? According to the team in Nobel Prize, there's no Indonesian has announcement in Nobel Prize. What's the problem? Because we have a lot of university from Indonesian, but no one from has a Nobel Prize. The problem is mostly all the teacher, a lecturer in university don't teach creativity to the student. That's the problem. Why we have don't have creativity in student. But I know I teach them for creativity. It is difficult. Even we know that it's like you said, it's useless this time, but might be for the future. But the problem is not just the result, the product, but the problem is the creativity. How to teach creativity to the student? That's the
Right.
problem. Yeah.
Right.
Yeah.
It's very difficult. One of my PhD students, Betsy Stretch, who Desi knows quite well, is doing her dissertation around creativity in STEM and looking at ways that we can do creativity innovations in that work. So we're starting to try and look at that. It's difficult to do, but more than anything, it's difficult to assess. Right? How we assess creativity is very difficult. We know it when we see it, but we don't know how to measure it, right? So as researchers, I think that's going to be one of the big challenges for us in integrated STEM is how do we measure these things? We know we value them, we value collaboration, we value creativity, but we have to be able to assess them. And we're not very good at that yet. So
Yeah. Is there any question to Professor Jill? Pano? Okay. Student? Yeah, we don't have teachers, alumni from the session. Instead, Mujakar. That's alumni from chemistry education department. We don't have a teacher come from this meeting, coming to this meeting. There any question to Professor Jill? Thank you very much, Jill, for your course in STEM problem. The title
thank
is
you for inviting me. I appreciate it.
yes. Okay. Okay. Thank you very much. Have a question or just put from head of department. Pak Pendi is head of department. This chemical education.
Well, thank you very much for the speaker and moderator. Hopefully what is conveyed can be useful for all of us. Ladies and gentlemen, finally we get to the last session of this event. To close today's event, we will invite Dr. Effendi, Magister of Science as the coordinator of Chemistry Education Study Program, Faculty of Teacher Training and Education, Sriwijaya University, to deliver his closing remarks.
Baik, thank you. Good evening, Mr. Jill, and thank you your presentation in this morning about STEM. Bapak Ibu hadirin yang saya hormati, dengan selesainya acara penyampaian presentasi oleh Prof. Jill from US dan discuss about this morning about STEM problem, and maybe thank you, Prof. Jill, and I close this meeting about STEM this morning. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much for Professor Julian Rowick and all of the audience of this event. I'm as the master ceremony, I apologize for any mistakes and thank you very much for your great attention. Good day and wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Jill.
warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera untuk kita semua. Yang terhormat, Dekan Fakultas Keguruan dan Ilmu Pendidikan Universitas Sriwijaya, Bapak Dr. Hartono MA. Yang terhormat, Wakil Dekan 2 Fakultas Keguruan dan Ilmu Pendidikan Universitas Sriwijaya, Ibu Dr. Nyimas Aisyah MSI PhD. Yang terhormat, Ketua Jurusan Pendidikan MIPA, Bapak Dr. Ketang Wiono MPD. Yang terhormat, Koordinator Program Studi di lingkungan Fakultas Keguruan dan Ilmu Pendidikan Universitas Sriwijaya. Yang terhormat, Bapak Dr. Effendi MSI selaku Koordinator Program Studi Pendidikan Kimia Fakultas Keguruan dan Ilmu Pendidikan Universitas Sriwijaya. Yang terhormat, Bapak Ibu Dosen Fakultas Keguruan dan Ilmu Pendidikan Kimia, baik yang hadir di tempat maupun yang mengikuti kegiatan secara daring, serta seluruh panitia dan peserta pada hari ini. Alhamdulillah, puji syukur kita haturkan karena berkat rahmatnya kita dapat berkumpul bersama di Aula Pasca Sarjana FKIP Universitas Sriwijaya Bukit Besar, Palembang, dalam rangka Purnabakti pelepasan dosen program studi pendidikan kimia, Bapak Dr. Andes JJ Mujamil MSI. Semoga kita selalu diiringi rahmat dan karunia-Nya agar acara pada pagi hari ini dapat terlaksana dengan baik. Sebelum memulai acara, izinkan saya selaku pembawa acara pada pagi hari ini untuk menyampaikan susunan acara. Yang pertama adalah pembukaan, yang kedua sambutan, yang ketiga ungkapan hati, yang keempat penyerahan cendera mata, yang kelima doa, dan yang terakhir adalah penutup. Agar acara pada pagi hari ini berjalan dengan lancar, marilah kita melafazkan lafaz basmalah. Selanjutnya adalah sambutan. Sambutan akan disampaikan oleh Ibu Dr. Nyimas Aisyah MSI PhD. Kepada Ibu dipersilakan.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sehat untuk kita semua. Yang saya hormati Bapak Ketua Jurusan Pendidikan MIPA FKIP UNSRI, Bapak Dr. Ketang Wiono. Yang saya hormati Bapak Koordinator Program Studi Pendidikan Kimia, Bapak Dr. Effendi. Yang saya hormati hadir di sini ada Bapak Profesor Pak Fuad, kemudian Pak Profesor Tatang, Bapak Ibu dosen di program studi pendidikan kimia yang sempat hadir secara daring maupun secara luring, segenap panitia, wabil khusus yang saya banggakan Bapak Jejem yang hari ini tentu saja berbahagia, ya, sangat berbahagia sudah melepaskan semua beban yang selama ini diembannya. Pertama-tama, marilah kita panjatkan puji syukur kehadirat Allah Subhanahu wa Ta'ala, karena di pagi hari ini kita masih diberikan kesehatan, kesempatan untuk sama-sama berkumpul di sini dalam rangka melaksanakan kegiatan Purnabakti. Sahabat kita, dosen kita, orang tua kita, Bapak Jejem. Ya, Purnabakti ini adalah suatu keniscayaan. Ya, kita semua akan mengalaminya. Saat ini yang mengalaminya adalah Pak Jejem. Ya, kemudian dalam waktu yang tidak lama lagi akan menyusul satu persatu dosen-dosen di FKIP UNSRI ini akan mengalaminya juga, termasuk saya. Ya, nah Pak Jejem beruntung. Pak Jejem beruntung karena di akhir masa jabatannya masih sehat, masih segar, masih bisa berkiprah, baik di dunia pendidikan maupun di keluarga. Ini suatu keberuntungan yang luar biasa. Kita tahu ya, banyak sahabat-sahabat kita, banyak dosen-dosen kita yang tidak sempat merasakan yang namanya Purnabakti. Kita baru saja kehilangan Pak Iceng, kehilangan Bu Betty, Kalau di kami itu Pak Budi Santoso, banyak sekali sudah dosen yang mendahului kita. Bu Harlina yang terbaru ya. Ya walaupun kita tahu beliau sakit, tapi tetap saja itu merupakan suatu berita yang mengejutkan bagi kita, kehilangan sahabat-sahabat kita yang belum sempat memasuki masa Purnabakti. Nah, Pak Jajem bisa memasuki ini dalam keadaan yang masih sehat. Atas nama pimpinan Pak Jajem, kami tentu saja mengucapkan terima kasih dan apresiasi yang setinggi-tingginya atas partisipasi Pak Jajem selama ini. Kami tahu Pak Jajem ini dosen yang sangat dibanggakan, diteladani oleh mahasiswa-mahasiswanya. Kita tahu tidak ada sedikit pun coretan-coretan jelek yang dialami oleh Pak Jajem. Ini suatu keberuntungan juga. Alhamdulillah, benar-benar alhamdulillah, bersih sampai masa akhir jabatan. Harapan kita semuanya seperti itu. Ya, kita semua berharap sampai nanti kita Purnabakti, kita tidak meninggalkan hal-hal yang jelek. Hal-hal yang jelek baik di mata dosen, di mata mahasiswa, maupun sivitas akademika FKIP UNSRI. Jadi sekali lagi Pak Jajem, kami mengucapkan terima kasih. Apa-apa yang sudah selama ini Bapak berikan kepada mahasiswa, itu insya Allah akan menjadi teladan bagi mahasiswa. Kedisiplinan Bapak, kerja keras Bapak. Yang paling menonjol bagaimana sifat agamis dari Pak Jajem. Ya, ini juga tidak dimiliki oleh semua dosen. Pak Jajem luar biasa. Jadi selanjutnya Pak Jajem juga, kami juga masih berharap, sangat berharap Pak Jajem tetap membuka hati untuk tetap bersilaturahmi kepada kami. Pintu fakultas ini kami buka selebar-lebarnya kepada Pak Jajem untuk kalau ada kegiatan menghadirinya. Pak Effendi ini diundang terus, ini buktinya Pak Fuad masih tetap diajak pada kegiatan ini. Artinya apa? Kekeluargaan di program studi pendidikan kimia ini masih kuat sekali. Jadi silakan saja Pak Jajem, kalau misalnya ada hal-hal yang bisa disumbangkan kepada kami, pikiran, itu kami akan terima dengan seluas-luasnya. Apalagi duit ya. Ya. Itu Pak Effendi itu menutup itu, buka keran seluar ya Pak ya, dibuka keran sebesar-besarnya. Kalau Pak Jajem mau ada bantuan apapun silakan. Bercanda Pak. Ya. Iya, dari Prodi juga Pak Jajem juga mudah-mudahan tidak keberatan kalau misalnya nanti dimintai sumbang saran terutama yang berkaitan dengan bidang ilmunya. Karena bidang ilmu Pak Jajem ini barangkali saat ini sudah berkurang. Ya, satu orang ahli sudah berkurang, ini masalah bagi Prodi Kimia. Entah kapan bisa ditambah lagi pengganti untuk di bidang itu. Atas nama pimpinan juga kami menyampaikan permohonan maaf yang sebesar-besarnya apabila selama ini baik kami pimpinan maupun barangkali dosen, mahasiswa, saya yakin, seyakin-yakinnya masih banyak kami di antara kami yang melakukan kesalahan, baik itu dalam tutur kata, dalam perbuatan yang barangkali membuat Pak Jajem kecewa. Atas nama semuanya nih, saya menyampaikan permohonan maaf yang sebesar-besarnya. Mudah-mudahan setelah ini ya kiprah Pak Jajem itu baik di keluarga maupun di luar itu semakin berkibar. Kami tunggu bagaimana aktivitas Bapak yang bisa semakin mengharumkan FKIP ini, khususnya program studi pendidikan kimia. Itu saja yang bisa saya sampaikan. Sambutan singkat, karena kata Pak Anom ini mau kejar-kejar, mau Jumatan Pak ya. Ya, saya juga mohon maaf apabila dalam kata sambutan ini tidak mewakili pimpinan. Atas nama pribadi saya mohon maaf. Saya akhiri. Billahi taufik wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Ibu atas sambutannya. Selanjutnya adalah ungkapan hati. Ungkapan hati yang pertama akan disampaikan oleh mahasiswa yang akan diwakili oleh Bupati HMK. Kepada Adi Hermawan selaku Bupati HMK dipersilakan.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera untuk kita semua. Yang terhormat Dekan Fakultas Keguruan dan Ilmu Pendidikan Universitas Sriwijaya, Bapak Dr. Hartono. Yang terhormat Wakil Dekan 2 Fakultas Keguruan dan Ilmu Pendidikan Universitas Sriwijaya, Ibu Dr. Anda Nyimas Aisyah. Yang terhormat Ketua Jurusan Pendidikan MIPA, Bapak Dr. Ketang Wiono. Yang terhormat Koordinator Program Studi di lingkungan Fakultas Keguruan dan Ilmu Pendidikan Universitas Sriwijaya. Yang terhormat Bapak Dr. Effendi selaku Koordinator Program Studi Pendidikan Kimia Fakultas Keguruan dan Ilmu Pendidikan. Yang terhormat Bapak Ibu Dosen Fakultas Keguruan dan Ilmu Pendidikan, Fakultas Keguruan dan Ilmu Pendidikan, serta seluruh panitia yang hadir pada hari ini. Salawat beserta salam semoga terlimpah curahkan kepada Nabi Agung kita, Nabi besar Nabi Muhammad Sallallahu Alaihi Wasallam. Pertama-tama kami ucapkan terima kasih atas kesempatan diberikan kepada saya pada pagi hari ini untuk menyampaikan sedikit ungkapan hati kami dari mahasiswa terkhusus program studi pendidikan kimia. Saya Adi Hermawan selaku Bupati Himpunan Mahasiswa Kimia ingin mengucapkan banyak terima kasih kepada Pak Jejem yang selama ini selalu sabar serta ikhlas memberikan ilmunya kepada kami. Segala ilmu dan kebaikan yang telah Bapak berikan, semoga ilmu tersebut bisa berguna untuk kami di kemudian hari. Kami sangat bersyukur menjadi mahasiswamu. Sebagai seorang dosen, engkau tidak hanya mengajarkan kami, tapi juga mendidik kami dengan penuh kasih sayang. Terima kasih untuk semua dedikasimu. Terima kasih untuk semua pengorbananmu serta pengorbananmu selama mendidik kami. Terima kasih juga untuk seluruh perhatianmu pada kami. Engkau guru terbaik. Serta kami memohon maaf yang sebesar-besarnya apabila selama Bapak memberikan ilmu kepada kami banyak melakukan kesalahan, kehilafan, baik yang disengaja maupun yang tidak disengaja. Mungkin itu saja yang dapat saya sampaikan. Saya akhiri, wabillahi taufik wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Adi Hermawan. Ungkapan hati selanjutnya akan disampaikan oleh Bapak Dr. Effendi MSI selaku Koordinator Program Studi Kimia. Kepada Bapak Effendi dipersilakan.
Terima kasih. Assalamualaikum warahmatullahi wabarakatuh. Ibu Nyimas Aisyah, Wakil Dekan 2 yang kami hormati, Ketang Wiono, Ketua Jurusan yang kami hormati, Bapak Ibu Dosen Program Studi Pendidikan Kimia yang kami banggakan, alumni, terkhusus Pak JJ Mujamil pagi hari ini yang kelihatan cerah sekali. Alhamdulillah, dan adik-adik, saudara-saudara mahasiswa yang kami banggakan. Pertama, mari kita sampaikan puji syukur kehadirat Allah Subhanahu wa Ta'ala, di mana pagi menjelang siang hari ini kita tetap dapat berkumpul di ruang aula pasca sarjana FKIP dalam rangka acara pelepasan dosen kita, termasuk saya jadi guru saya sebetulnya, sahabat koleha kita. Pada pagi hari ini pada tanggal 19 Juli yang lalu beliau sudah habis masa tugasnya, tapi seperti yang Bu Nima sampaikan, kami tetap berharap nanti Pak Jaja masih bisa menyampaikan atau memberikan sumbangsi kegiatan baik akademik, karena terus terang aja untuk dosen kimia analitik berkurang satu Bu kami. Nanti kalau yang kemarin telah berangkat Pak Iceng, Bu Betty yang bidang pendidikannya, kemudian 2024 nanti akan ada lagi 2025 termasuk saya barangkali. Bapak Jejem yang kami hormati, pertama kami sampaikan terima kasih karena telah bergabung mulai dari saya menjadi mahasiswa sampai dengan akhir masa jabatan Bapak. Dan seperti yang Bu Nyimas sampaikan, bahwa banyak cerminan yang dapat kami anut, kami ikuti, kami pedomani, bahkan mungkin bisa diterapkan baik secara karakter Bapak menyampaikan di program studi pendidikan kimia yang sudah sangat lama sekali, dan itu hal yang sangat kami banggakan. Kemudian juga kami mohon maaf Bapak, andai kata ada hal yang kurang berkenan atas nama rekan-rekan dosen maupun juga mahasiswa. Kadang-kadang mahasiswa itu macam-macam tingkahnya, jadi tapi Pak Jejem sebetulnya sudah sangat memaklumi, beliau sampaikan. Bapak Ibu hadirin yang kami hormati, jadi atas nama program studi pendidikan kimia menyampaikan ucapan terima kasih atas pengabdian yang telah disampaikan oleh Bapak, dan juga cerminan yang mungkin dapat kami ambil dari baik secara karakter Bapak selama di program studi pendidikan kimia sebagai koleha dan juga sebagai dosen, terutama bagi saya pribadi. Baik Bapak Ibu, demikian, lebih dan kurang sekali lagi saya mohon maaf, dan kepada Allah mohon ampun. Wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Bapak Effendi. Ungkapan hati selanjutnya akan disampaikan oleh Bapak Dr. Andes Zulfakar MSI selaku perwakilan dari alumni. Kepada Bapak dipersilakan.
Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, alhamdulillahillazi ansala al abdihil kitaba wa lam yaj'al iwaja. Asyhadu an la ilaha illallah wa la syarikalah wa asyhadu anna Muhammadan abduhu wa rasuluh nabiyya ba'da. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amma ba'd. Yang kami hormati Dekan FKIP UNSRI Sriwijaya, Bapak Dr. Hartono MPD, yang diwakili oleh Wakil Dekan 2 Bidang Akademik dan Umum, Ibu Dr. Anda Nimas Aisyah MSI PhD. Kemudian yang kami hormati juga Ketua Jurusan Pendidikan MIPA, Bapak Dr. Ketang Wijaya MPD. Ya, Ketang Wiono Pak, maaf Pak kalau salah. Kemudian kami sampaikan juga yang terhormat kepada Bapak Koordinator Prodi Kimia, Bapak Dr. Effendi Nawawi MPD, MSI Pak maaf. Kemudian yang kami hormati Bapak Ibu dosen yang kami sebutkan Profesor Dr. Andes Tatang Suheri MA, ini juga adalah guru saya SMA Pak. Jadi saya juga berteladan dengan Bapak Tatang juga ini. Kemudian yang kami hormati juga Bapak dosen, Ibu, yang saya tidak dapat sebutkan saya satu persatu, dan khususnya kami sampaikan kepada Bapak dosen kami, dan kami juga Bapak Dr. Bapak Dr. Andes Jejem Mushamil MSI, maaf Pak kalau salah. Kemudian pengurus serta alumni Prodi Kimia, sebenarnya sudah saya undang ada 10 orang Pak. Yang 10 orang itu barangkali sedang kebenaran ini ada akreditasi. Jadi barangkali ada yang mungkin datang, kalau nanti mereka sempat datang akan hadir. Saya sudah menelepon juga. Karena mereka juga banyak yang tadi bertanya, ada yang mau datang ke sini, sangkanya di sini adalah FKIP Ogan. Saya juga sempat salah juga tadi masuk ke gedung FKIP sana, ada manajemen. Ternyata ini adalah gedung khusus FKIP untuk pasca sarjana. Ya, saya mohon dimaklumin. Kemudian mahasiswa prodi, adik-adik yang kami cinta, kami sayangin, yang insya Allah dirahmati oleh Allah Subhanahu wa Ta'ala. Bapak Ibu yang kami hormati, saya perkenalkan sebelumnya, saya adalah mahasiswa angkatan 85. Kemudian lulusan tahun 1990, itu satu angkatan dengan Bapak Dr. Madis Koryawan MSI juga PhD, yang saya banggakan. Saya juga honor lama Pak di beberapa swasta. Begitu saya tamat langsung honor di beberapa swasta, dan 13 tahun kemudian saya baru diangkat menjadi PNS. Alhamdulillah Bu. Diangkat itu juga karena banyak rival untuk yang ke prodi kimia ini. Kimia ini rivalnya adalah S1 teknik yang dapat PPG. Demikian juga dari SSI dapat PPG. Jadi untuk jam untuk kimia itu sangat sedikit sekali. Jadi saya waktu sertifikasi juga banyak mengajar di luar. Itu pun kadang-kadang hanya mengambil supaya cukup 24 jam saja. Dan kenangan saya banyak di FKIP UNSRI ini, terutama dengan bapak-bapak dosen, termasuk Bapak Dr. Andes Jeje Mujamil, Bapak Tatang, Bapak Effendi, Pak Satria Sanjaya, kemudian Pak Anom, terutama Pak Madi. Terus yang paling saya sayangin juga Pak Arif Rahman Hakim. Ini adalah pernah PA saya juga, PA saya ketika saya mahasiswa. Alhamdulillah beliau cukup baik dengan mahasiswa-mahasiswa. Kemudian alhamdulillah syukur saya pada kesempatan ini mohon izin ini kepada Pak Satria, ini alumni tertua ini di UNSRI, pernah juga ketua alumni kimia, Ikatan Mahasiswa Kimia atau alumni juga. Dan saya adalah saat ini adalah, mohon maaf untuk menyampaikan ini, seandainya nanti pas saya sampaikan ini itu baik, itu adalah datang dari Allah Subhanahu wa taala, dan ada seandainya nanti ada yang tidak berkenan, itu mungkin datangnya dari saya sendiri. Selanjutnya pada kesempatan ini saya juga mengucapkan terima kasih atas undangan dan diberikan kehormatan untuk menyampaikan kata sambutan selaku mewakili Ikatan Alumni Prodi Kimia yang masa kerjanya tahun 2019 sampai 2023. Jadi masa ini saya pada saat ini sudah melaksanakan sekali kegiatan kegiatan sejenis seminar, kegiatan penulisan karya tulis. Kemudian di masa pandemi, jadi kegiatan-kegiatan sempat tertunda, jadi tidak bisa melaksanakan kegiatan-kegiatan lainnya, dan selalu berkaitan dengan MGMP kami Kimia dan Fisik Kimia, dan MGMP provinsi maupun MGMP kota. Jadi kadang-kadang untuk menyatukannya itu agak susah. Ketika kami mengikatkan kegiatan MGMP kota, MGMP provinsi, akibatnya nanti tidak kami adakan lagi MGMP yang lainnya. Tapi baru-baru ini kami sudah melaksanakan tadi MGMP provinsi, dan saya ingin mengaitkan ke alumni juga sebenarnya di sana. Saya diundang semua kepada seluruh alumni. Hanya sekedar webinar saja itu kami laksanakan. Kembali lagi pada ucapan terima kasih undangan tadi, dan kami ucapkan kembali terima kasih kepada dosen, Bapak Ibu dosen yang telah kami dibekalin daripada pengetahuan, khususnya kepada Bapak Dr. Andes Jejem Muzamil yang telah memberikan ilmunya, terutama bapak-bapak yang lainnya, dan juga kami mengucapkan terima kasih kepada Bapak Jejem juga yang telah menjadi orang tua kami, menjadi dosen yang luar biasa, dan menjadi sahabat kami pada saat kami masih kuliah, dan mudah-mudahan akan menjadi suatu inspirasi bagi kita semua, baik adik-adikku mahasiswa Prodi Kimia maupun para dosen di Prodi Kimia maupun di prodi-prodi yang lainnya. Dan kami ucapkan terima kasih juga atas ketulusan hati beliau, khususnya Pak Jejem Muzamil, telah mengukir sejarah atau di hati masing-masing, baik kepada adik-adik prodi, pada kami juga, pada alumni angkatan dari tahun 90 kami sudah kenal itu Pak Jejem, sudah ini 82 Pak Jejem masih Pak Jejem 87 masih Pak Jejem sempat mengajarkan kami ya. Jadi kami mengukir sejarah, dan kami lihat kesederhanaan beliau dan ketulusan hati beliau dalam memberikan keteladanan. Yang keteladan inilah sebagai untuk menjadikan suatu lentera hati bagi kepada junior-juniornya dan kepada kita sebagai alumni, sebagai mahasiswanya, dan akan menjadi keteladan yang perlu diteladanin. Selanjutnya kami ucapkan juga selamat yang telah memasukin Purnabaktinya Pak Jejem, masih dalam keadaan sehat seperti yang disampaikan oleh Ibu Nimas dan Pak Effendi tadi. Alhamdulillah, syukur masih diberikan Allah dalam barokahnya, dan selamat menikmati hari bersama keluarga. Semoga silaturahim dan semoga komunikasinya tetap terjaga, baik kepada para dosen-dosen yang masih bertugas maupun daripada alumni-alumni yang saat ini tersebar di mana saja berada. Dan selanjutnya kami mohon maaf apabila atas segala kekurangannya, salah ucap, kemudian salah pilihan kata, kemudian salah sikap yang selama ini ataupun yang saya sampaikan ini juga tidak berkenan, karena mewakili daripada mahasiswa, mewakili daripada alumni-alumni yang tidak sempat saya sapa seluruhnya. Hanya beberapa saja saya konfirmasi kehadirannya dan kesiapannya. Saya sudah langsung saya undangkan sampai ke Ibu dia melalui Pak Effendi juga, dan mudah-mudahan mereka hadir. Dan terakhir kepada Allah saya mohon maaf ampun kepada Bapak Ibu kalau ada kesalahan kami minta maaf. Saya sampaikan untuk pantun untuk kita semua, untuk yang tadi ada materi pertama adalah kuliah umum dari Jakarta ke Palembang untuk berbagi ilmu dan pengalaman. Harapan saya selaku alumni IKP Prodi Kimia untuk mahasiswa Prodi UNSRI, khususnya Prodi Kimia, jadilah anak bangsa, jadikan harapan anak bangsa. Dan satu lagi saya minta penuntun sekali lagi untuk hubungan dengan Purnabakti ini, pohon palem ada di simpang 3. Jangan lupa buahnya tolong dibawa. Meskipun kita akan berpisah raga, namun tetaplah bersatu dalam jiwa. Saya akhirin, saya tutup billahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih atas ungkapan hati dari Bapak Zulfakar. Ungkapan hati selanjutnya akan disampaikan oleh Bapak Dr. Ketang Wiono MPD selaku Ketua Jurusan Pendidikan MIPA. Kepada Bapak dipersilakan.
Baik, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Bapak Ibu dosen, ini sebagian besar adalah dosen-dosen saya yang saya hormati, dan adik-adik mahasiswa yang berbahagia. Tentu atas nama jurusan Pendidikan MIPA, kami menghaturkan ribuan terima kasih yang setinggi-tingginya kepada Pak Jejem. Pak Jejem ini sudah saya anggap secara pribadi adalah orang tua saya, gitu ya. Ketika saya menjadi korprodi, saya sering berkomunikasi nih dengan Pak Jejem, ya, sering mendapatkan banyak teladan dan nasihat dari Pak Jejem, sehingga barangkali kalau dilihat di jurusan Pendidikan MIPA saat ini jumlah dosennya ada 73, ya. Jadi kehilangan sosok Pak Jejem ini saya kira suatu kerugian besar bagi jurusan, bukan hanya bagi prodi pendidikan kimia. Ya. Karena sosok beliau yang saya tahu, ya, tidak pernah yang namanya tadi Bu WD2 mengatakan bebas dari coret-coretan, gitu ya. Kalau saya lebih cenderung belum pernah saya mendengar beliau protes atau apalah gitu ya di tingkat jurusan ini. Beliau memberikan contoh yang nyata seperti itu. Ya. Memberikan contoh yang nyata sampai kenangan saya Pak Jejem barangkali ya, ketika saya menyusun jadwal, saya diingatkan dengan Pak Jejem. Ini nabrak Pak? Sholat zuhur gitu ya rasanya Pak Jejem ya. Nah, itu jarang-jarang sekali Bapak Ibu. Ya, kadang-kadang sebagai seorang korprodi itu menyusun jadwal itu ya yang penting 3 SKS, 2 SKS seperti itu ya. Tapi saya sadar ya ketika Pak Jejem saat itu mengampu mata kuliah kimia dan selalu nampaknya di fisika ya Pak Jejem ya, spesialis. Jadi saya atas nama ketua jurusan dan sekaligus dosen-dosen di Prodi Pendidikan Fisika dan mahasiswa Pak Jejem yang tidak sempat hadir pada pagi hari ini, mewakili Prodi Pendidikan Fisika juga menyampaikan ribuan terima kasih. Barangkali kalau ilmu itu bisa dicari, bisa dibaca di buku Pak Jejem. Tapi keteladanan Pak Jejem ketika menjadi dosen itu yang tidak ada di buku. Ya, tidak ada di buku. Karena saya yakin banyak mahasiswa bahkan dosen-dosen juga yang terinspirasi dengan keteladanan Pak Jejem ini. Ya. Saya tahu ketika kuliah luring dulu tidak telat tuh sholat, walaupun sholatnya karena di gedung D yang lebih dekat adalah ke Fasilkom ya Pak ya. Ya nggak apa-apa gitu ya. Jadi seperti itu kenangan untuk Pak Jejem. Jadi atas nama jurusan Pendidikan MIPA, kami mengapresiasi pengabdian Pak Jejem yang luar biasa ini. Mudah-mudahan Pak, segala ilmu yang Bapak berikan, baik untuk mahasiswa maupun untuk kolega, itu bernilai ibadah di sisi Allah Subhanahu wa Ta'ala. Dan kalaupun ada silaf, barangkali perkataan, perbuatan, sebelum Pak Jejem minta maaf, kami sudah memaafkan Pak. Ya, jadi kami semuanya sudah memaafkan, mengikhlaskan. Mudah-mudahan Pak Jejem bisa menikmati masa-masa Purnabakti ini dengan bahagia. Tentu saya nggak tahu masih di Palembang atau mau pulang ke masih di Palembang ya Pak ya mungkin ya. Nah, jadi barangkali kita masih bisa bersilaturahmi dengan Pak Jejem ini. Barangkali itu saja yang dapat saya sampaikan. Sekali lagi terima kasih Pak Jejem atas pengabdiannya, dan mohon walaupun sudah pensiun nanti kalau ada apa-apa saya ditelepon Pak, kalau misalnya ada masukan, saran dan lain sebagainya. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Bapak Ketang. Ungkapan hati selanjutnya adalah ungkapan hati yang paling kita tunggu, yang akan disampaikan oleh Bapak Dr. Andes JJ Mujamil MSI. Oh ya, mohon maaf. Selanjutnya adalah ungkapan hati yang akan disampaikan oleh Bapak Pak Tatang Soheri PhD. Silakan kepada Bapak.
Assalamualaikum warahmatullahi wabarakatuh. Yang saya hormati PD2, kemudian Ketua Jurusan, Sekretaris Jurusan. Saya di sini mewakili dosen-dosen ya. Kalau tadi ada yang kenal dengan Pak Jejem tahun 87 sampai ke bawah, saya itu kenal dengan Pak Jejem itu dari kami cari ke pending. Jadi calon mahasiswa tahun 78. Saya sudah kenal dengan Pak Jejem. 78 itu di rumah Pak Jejem itu kami cari ke pending karena diwajibkan kami bawa ke pending. Saya masih ingat waktu itu disuruh mencari ke pending laki-laki dan perempuan. Susah memang Tapi karena senior ya kita turut apa saja yang kata senior. Katanya gampang katanya mencari ke pending laki-laki atau perempuan. Dekatkan saja kalau yang laki-laki di atas. Sampai sekarang itu masih ingat saya itu. Kata senior itu katanya kalau didekatkan katanya laki-laki pasti di atas katanya. Yang perempuan pasti di bawah katanya. Iya. Nah jadi tahun 78 saya masuk ke IKIP Bandung sama-sama Pak Jejem cari ke pending kami malam-malam. Ya waktu itu semalam itu ada foto Pak Jejem dengan saya yang rombongan. Kami sedang di Posma pakai topi karton. Semalam barusan ketemu foto itu ya. Jadi kemudian Pak Jejem datang ke UNSRI tahun berapa? Tahun 1982. Yang Pak Jejem temui adalah saya karena kami duluan. Waktu itu Pak Anom, Pak Iceng, Bu Betty, Pak Wisnu, angkatan saya, kami masuk ke Prodi Kimia tahun 82 ya. Waktu itu Pak Fuad sudah senior di jurusan. Walaupun beda tahun aja ya. Pak Pendi, kemudian Pak Sanjaya, yang lain-lain itu masih mahasiswa ya. Tahun itu ya, tahun kami datang ke UNSRI. Nah, Pak Jejem itu yang dicarinya saya, artinya memang kami sudah lama kenal gitu ya. Pak Jejem datang ke UNSRI ya, tahun 82. Jadi dengan Pak Jejem saya cukup lama kemudian sama-sama jadi dosen sampai hari ini, katakanlah Purnabakti pensiun Pak Jejem. Jadi saya sudah lama kenal Pak Jejem. Jadi tahun 78 saya sudah mengenal Pak Jejem. Kemudian sampai hari ini tahun 2022 ya. Jadi apa namanya cukup lama. Mudah-mudahan kita seperti Pak Jejem waktu pensiun itu masih sehat ya. Apa namanya? Tahun ini memang Pak Jejem, tahun 2024 Pak Anom, kemudian apa namanya Pak Arif itu ya, apa namanya nanti 2025 katanya Pak Pendi. Tinggal waktu ya. Jadi waktu Pak Jejem, sekarang Pak Jejem pensiun, nanti giliran kami. Atas nama teman-teman, mohon maaf kalau ada salah Pak Jem. Tentu. Ya Pak Jem dosen yang baik. Semoga bisa mengasuh cucung Pak Jem ya. Sekarang ini yang kita banggakan itu cucung ya. Saya tadi bilang WD2 barusan ketemu cincin saya itu gara-gara cucung ya. Cucung saya sekarang sedang di Padang. Jadi terima kasih Pak Jem. Kami kehilangan Pak Jem. Di fisikanya saya yang mengajar kimia dasar Pak Ketang, ganti Pak Jem. Apa namanya? Sekali lagi selamat Pak Jem. Assalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Bapak Tatang atas ungkapan hatinya. Ungkapan hati yang terakhir akan disampaikan oleh Bapak Dr. Andes Jejem Mujamil MSI. Kepada Bapak Jejem dipersilakan.
Assalamualaikum warahmatullahi wabarakatuh. Nah, alhamdulillah nahmadu wa nusalli ala rasul karim. Allahumma sholli wa sallim wa barik ala sayyidina Muhammad. Yang paling utama adalah kita selalu mengucapkan segala puji bagi Allah Subhanahu wa taala. Alhamdulillah. Segala sesuatunya karena Allah SWT. Apa yang telah saya capai tidak lain adalah karena kasih sayang Allah SWT. Saya bisa menyelesaikan tugas sampai Purnabakti ini ya sebetulnya atas kasih sayang Allah. Apapun keadaannya, sehat, sakit dan sebagainya, karena Allah SWT. Jadi segala puji kita sampaikan kepadanya. Apa yang telah kita capai bukan kekuatan saya sendiri gitu ya, atas ego sendiri, bukan, karena tadi atas kasih sayang Allah Subhanahu wa taala. Jadi segala apa yang kita jalani, apa yang kita tempuh dalam kehidupan sehari, dalam melaksanakan tugas dan sebagainya, tidak lain atas petunjuknya. Maka segala apa yang telah kita capai kita kembalikan kepadanya. Bapak Ibu hadirin rahimakumullah, dari atas berakhirnya saya bertugas di fakultas ini, yang pertama dan utama saya mengucapkan banyak terima kasih atas kebersamaan kita semua ya, dari fakultas, dari lembaga, dari sahabat-sahabat, dari kawan-kawan atas kebersamaan bersama ya, kebersamaan kita. Dan yang tadi yang paling penting adalah saya mohon maaf yang sebesar-besarnya. Tentunya saya secara pribadi belum bisa secara optimal, secara maksimal dalam pengabdian ini. Begitupun kepada mahasiswa ya, mungkin saya belum optimal, belum maksimal. Dan itu saya rasakan sekarang. Setelah Purnabakti ini ada evaluasi kenapa kita saya sendiri mengevaluasi, saya merasa belum maksimal, belum optimal, tapi itulah perjalanan yang yang sudah kita tempuh ya, tidak bisa diulangi lagi kan. Hanya mungkin saya berpesan kepada mahasiswa, juga kepada kawan-kawan saya, bagaimana supaya tidak di kemudian hari itu menyesal seperti apa yang terus terang saja saya masih ada semacam penyesalan dalam arti kata mungkin bekerja masih terlalu dominan oleh pemikiran ya, belum oleh kesadaran. Coba kalau yang membantu adalah kesadaran kita, mungkin kita akan merasa puas gitu ya, merasa. Mungkin itu saja yang bisa saya sampaikan. Yang utama adalah saya mohon maaf kepada semua mahasiswa, kemudian alumni, kemudian rekan-rekan saya, kemudian dari atasan-atasan saya ya, dari staf dekan, dari jurusan prodi ya, saya mohon maaf ya, saya belum bisa memberikan kinerja yang optimal tadi, yang maksimal tadi ya, dan apa yang kesalahan-kesalahan, ada kehilapan mohon dimaafkan. Itu saja yang dapat saya sampaikan. Bila ifissabillah, wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Bapak JJM atas ungkapan hatinya. Acara selanjutnya adalah penyerahan cenderamata. Penyerahan cenderamata yang pertama akan diserahkan oleh pihak jurusan kepada Bapak Dr. Andes JJM Mujamil MSI. Dan penyerahan cenderamata yang kedua yang akan diserahkan oleh pihak prodi. Dan yang terakhir adalah penyerahan cenderamata yang akan diserahkan oleh pihak alumni. Mohon maaf, yang terakhir adalah penyerahan cenderamata yang akan dilakukan oleh pihak mahasiswa. Baiklah, acara yang selanjutnya adalah pemotongan tumpeng yang akan dilakukan oleh Ibu Wakil Dekan 2, Ibu Dr. Anda Nyimas Aisyah MSI PhD dan diserahkan kepada Bapak Dr. Andes Jaja Mujamil MSI. Selamat Purnabakti kepada Bapak Dr. Andes Jaja Mujamil MSI.
Suatu hari dikala kita duduk di tepi pantai.
Baiklah, kepada seluruh dosen dan peserta yang hadir dipersilakan untuk bersalaman dengan Bapak Dr. Andes Jaja Mujamil MSI.
Kian menepi, burung camar terbang bermain di derunya air. Suara alam ini.
Salaman dari pihak Bapak Made. Salaman dari pihak Bapak Hadeli. Dari sahabat Bapak Arif.
Sinar surya perlahan mulai tenggelam.
Dari pihak Bapak Sanjaya.
Mengalunkan melodi tentang cinta. Ada hati
dari Bapak Rodi, Bapak Anom, dari dosen kita dari luar negeri Ibu Desi, jauh-jauh datang dari Amerika memberikan cenderamata untuk Bapak Dr. Andes Jaja Mujamil. Dan dari sahabat tercinta dari Bapak Profesor Tatang Suheri PhD. Dari sahabat dari Bapak Fuad. Dari Bapak Ketang. Dari Ibu Dia, Ibu Eka, Bapak Zulkafar,
Sementara sinar surya perlahan mulai tenggelam.
suara kita mengalunkan melodi tentang cinta.
Ada hati
kepada para mahasiswa untuk dipersilahkan untuk bersalaman kepada Bapak Dr. Andes Jaja Mujamil, MSI. Kepada Bapak Dr. Andes Jaja Mujamil MSI dipersilakan untuk duduk.
Jiwaku tentram di sampingmu, hatiku damai, jiwaku
Baiklah, acara selanjutnya adalah foto bersama. Kepada Bapak Ibu dosen dipersilakan untuk mengambil posisi.
Bapaknya alumni. Kita tak masuk alumni. Bapak alumni gitu. Kalau Desi rumah ini nanti.
Kepada para mahasiswa dipersilakan untuk mengambil posisi untuk berfoto bersama Bapak Dr. Andes Jaja Mujamil MSI.
air mata basahi pipimu di saat kita akan berpisah. Terucapkan janji padamu kasihku, takkan ku lupakan dirimu. Begitu beratnya kau lepas diriku, sebut namaku jika.
Baiklah, acara yang selanjutnya adalah doa bersama yang akan dipimpin oleh Bapak Dr. Andes M. Hadili LMSI. Kepada Pak Hadili dipersilakan.
Iya. Bapak Ibu yang kami hormati, mari sejenak kita bermunajat kepada Allah Subhanahu wa taala. Mudah-mudahan acara yang kita lakukan ini mendapatkan ridho dan keberkahan dari Allah Subhanahu wa taala. Amin ya rabbal alamin. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin, hamdan syakirin, hamdan na'imin, hamdan nu'afi ni'amahu yukafi majidah. Ya Rabbana lakal hamdu kama yanbaghi li jalalikal karim wa azimi sultanik. Allahumma salli ala sayyidina Muhammadin wa ala ali sayyidina Muhammad. Allahumma inna nas'aluka ridhaka wal jannah, na'udzubika min sakhatika wan nar. Allahumma innaka afun karim, tuhibbul afwa wa afu anna ya karim. Allahumma fir lana dzunubana wa kafir anna sayyi'atina wa tawaffana ma'al abrar. Allahumma fir lana wa li walidayna warhamhuma kama rabbayani shaghira wal jami'il muslimina wal muslimat wal mu'minina wal mu'minat al ahya minkum alamat bi rahmatika ya arhamar rahimin. Ya Allah, ya Tuhan kami, Allah yang Maha Pengampun, Maha Pengasih lagi Maha Penyayang. Ampunkanlah dosa kami ya Allah. Ampunkan dosa kedua orang tua kami. Ampunkan dosa anak dan istri kami ya Allah. Ya Allah, kami mohon kepadamu ya Allah. Pada hari ini kami berkumpul bersilaturahmi dalam rangka Purnabakti sahabat kami, dosen kami, Bapak Jajam Mujamil. Untuk itu kami mohon kepadamu ya Allah. Berikanlah sisa umur beliau, sisa umur kami mendapatkan ridho dan keberkahan darimu ya Allah. Jadikan sisa umur kami ini betul-betul hanya mengabdi dan menghamba kepadamu ya Allah. Jadikanlah sisa umur kami ini ya Allah untuk menambah nilai-nilai agama, nilai-nilai ibadah dan nilai-nilai ilmu kepadamu ya Allah. Rabbi sa'alni muqimas sholati wa min zuriyati rabbana wa taqabbal doa. Rabbi habli minas sholihin. Ya Allah, Tuhan yang Maha memberi petunjuk, berikanlah kekuatan kepada kami, kepada anak cucu kami, kepada penerus-penerus kami untuk meningkatkan nilai-nilai ibadah kepadamu ya Allah, untuk tidak meninggalkan sholat, untuk tidak meninggalkan ibadah-ibadah yang engkau ridhoi ya Allah. Ya Allah, pada hari ini juga kami berkumpul kepadamu ya Allah dalam rangka memperingati Purnabakti sahabat kami, dosen kami, Bapak Jajam Mujamil ya Allah. Untuk itu kami mohon kepadamu ya Allah, berikanlah kami kesehatan, berikanlah kami keberkahan sisa umur kami ini. Untuk itu kami mohon kepadamu juga ya Allah, jadikanlah sisa umur kami ini sisa umur yang selalu menambah nilai-nilai ibadah kepadamu ya Allah. Rabbi firli wali walidaina warhamhuma kama rabbayani shaghira. Rabbi firli wali walidaina warhamhuma kama rabbayani shaghira. Rabbi firli wali walidaina warhamhuma kama rabbayani shaghira. Rabbana hab lana min azwatina wa zurriyatina qurrata a'yun waj'alna lil muttaqina imama. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Fadinal jannata mal abror. Ya Aziz, ya Ghaffar, ya Rabbal Alamin. Sallallahu ala sayyidina Muhammadin nabiyyi wa ala alihi washabbihi wa barik wasalam. Subhana rabbika rabbil izzati amma yasifun. Wassalamu ala mursalin walhamdulillahi rabbil alamin. Taqabbalallahu minkum minkum taqabbarallah ya karim.
Terima kasih kepada Bapak Hadeli. Baiklah, untuk menutup acara kita pada siang hari ini, marilah kita bersama-sama membaca lafaz hamdalah. Terima kasih banyak kepada Bapak Dr. Andes JJ Mujamil MSI atas jasanya selama ini dalam mendidik mahasiswa dan menjadi tauladan bagi kita semua. Terima kasih kepada Bapak Ibu dosen dan peserta pada acara pada siang hari ini. Selaku pembawa acara, saya minta maaf atas kesalahan. Wassalamualaikum warahmatullahi wabarakatuh. Sekali lagi selamat Purnabakti kepada Bapak Dr. Andes JJ Mujamil MSI.
Aku tertarik dengan bajiran. Tadi kan pemimpin. Edwan. Edwan kasetnya. Pak masih.